All right, today we're going to pull back the curtain on one of the cleverest, most powerful data structures in all of computer science, the hash table. This is the secret sauce behind how your computer can find a needle in a haystack instantly.
So just think about it for a second. You go to log into a website, right? You type your username, hit enter, and bam, you're in. The system just found your specific profile out of maybe millions of others, and it did it in the blink of an eye. How in the world does that happen so fast? It's not actual magic, but it's pretty darn close. It's just some really, really clever engineering.
I mean, the slow way, the brute force way, would be to check every single user in the database, one by one. Is this you? Nope. How about this one? Nope. That's like trying to find a friend's number by reading a phone book starting from page 1. But the fast way, what computers actually do, is like knowing exactly what page to flip to. The real question is, how does it know?
And that is where this awesome data structure, called a hash table, comes into play. It's the genius behind this whole magic trick of instant lookups. So what is a hash table? You can think of it like a super smart filing cabinet. It stores everything in key-value pairs. So the key might be your username, and the value would be all your profile info. But the real secret weapon here is something called a hash function. This function takes your key, does a super quick calculation, and tells you the exact drawer, the exact memory address, where your stuff is filed.
Okay, let's walk through it. Let's say our key is the word apple. We take that word and we feed it into our hash function. The function does its thing, some quick math, and spits out a number. In this example, it spits out the number 3. That number is our index. It tells us, hey, the information for apple is in slot number 3. No searching, no guessing, we just go straight there.
And this right here brings us to what's basically the holy grail in computer science, something called constant time, or O1. What that means is, it doesn't matter if our table has 10 items or 10 million items. Finding what you're looking for takes the exact same tiny amount of time. That is what makes hash tables just unbelievably fast and scalable.
So there you have it, right? A perfect system. Instant lookups, problem solved. Our work here is done.
Well, maybe not. As it turns out, there's a little wrinkle, a tiny fly in the ointment that every single hash table has to deal with.
This is where we get to the main conflict in our story. What happens when our hash function, which seemed so perfect, gives 2 different keys the exact same spot? This, my friends, is called a hash collision. Imagine our function tells us apple goes in slot 3. Great. But then we try to add banana, and the function says, yep, that also goes in slot 3. Uh-oh. You can't put 2 different things in the exact same memory slot. Suddenly, our perfect system doesn't seem so perfect anymore. But don't worry. Of course, the brilliant people who came up with this stuff also came up with some really clever ways to fix this exact problem. Let's check out the 2 most popular strategies. First up, we've got a technique called chaining. The idea here is actually pretty simple. Instead of each slot holding just one thing, we make each slot a little bucket or a list. The analogy I love is a coat hook. If there's already a coat on hook number 3, what do? You just hang your coat right on top of it. So when a collision happens, we just add the new item to the list at that spot. Simple.
And if you look at the code, it's just as simple as it sounds. This little bit of Python, that .append command, it just means add this new key value pair to the end of the list at that specific index. It's a really elegant, effective fix.
Okay, so the second big solution is called linear probing. This one goes a completely different route. It doesn't use lists. Instead, it just says, okay, my spot is taken, no problem, I'll just check the next spot over. It's exactly like trying to find a parking space in a busy lot. Spot 3 is taken? Okay, let's look at spot 4. That one's taken? Fine, I'll check spot 5, and so on, until you find an empty space. And the code for this is also pretty clever. It basically just says, take the current index and add 1 to check the next spot. But the really cool part is that %sign, the modulo operator. All that does is make sure that if you get to the end of the parking lot, you just circle back around to the beginning and keep looking. It turns the whole thing into a circular search.
So let's put these 2 side by side. You've got chaining, our coats on a hook method, and you've got linear probing, the next open parking spot method. Now they both work, but they each have their own pros and cons, right? Chaining is pretty straightforward, but you might use a bit more memory creating all those little lists. Linear probing is great for memory,
But you can run into this thing called clustering, where filled spots clump together and slow down your search. Which one is better? Well, it really just depends on what you're building.
Okay, so this has been a lot of theory, which is cool, but where do you actually see this stuff? Let's talk about where hash tables pop up in the real world.
And the answer is literally everywhere. Seriously, if you used your phone today, if you went on a website, if you wrote a single line of code, you have benefited from the speed of a hash table. You just probably didn't know it.
And hey, for all you Python programmers out there, you use these all the time. You know the Python dict, the dictionary? That's a hash table. It's a super optimized, powerful hash table running on these exact principles we've been talking about. Every time you make a dictionary, you're wielding this magic.
So this here is a great little recap of the whole shebang. You start with hashing to turn your key into an index. If there's a collision, you use a solution like chaining to handle it. Insertion is just adding a new key value pair. Retrieval is that magical instant lookup we've been talking about. You hash the key, find the right spot, and grab your data. And of course, deletion is just removing something. These are the core operations that make it all tick. And the impact of this is just huge. It's way bigger than just Python dictionaries. Hash tables are the engine running under the hood of databases. They're what power the caches that make websites load in a snap. They're even how the tools that build our software understand the code we write. They are, without a doubt, a cornerstone of modern computing.
So, when you boil it all down, what's the big idea? It's all about a trade-off. Hash tables choose to use a bit more memory to get that mind-blowing speed. And that concept, trading one thing for another, memory for speed, simplicity for power, that's what computer science is all about. Which really makes you wonder, right? What will be the next great trade-off that defines the future of computing?